So now we're going to look at mechanical vibrations. And so let me go ahead and title this Mechanical Vibrations. Okay. And this is an application of second order differential equations, and we're going to use all the methods we've been studying in class to solve second order differential equations to assist us in making sense out of the set of equations we'll be given with our assumptions for this physical process. So we're going to take a look at mechanical vibrations, and in particular, we are going to look at a mass that is hanging from a spring. Okay, so let me go ahead and begin by drawing the system that we're going to be dealing with. So first and foremost, we're going to be dealing with a mass that is hanging from some form of spring. Okay, so here's our mass, designating it with an M. Okay, so mass hanging from a string. And also vibrations can occur in pretty much all branches of engineering. So this becomes a very important feature, especially when you're planning to build bridges. Vibrations play an enormous factor in considering the types of stress that the bridge is going to undergo. The same thing goes for mechanical engineers who have to design frames for a vehicle or the springs in your car, or another simple example could be the durability of a skyscraper. Even those have to oscillate under different weather conditions in order to have a certain flexibility and tenacity so they don't crumple or they don't implode on themselves. And buildings that are engineered correctly, at least those that meet code within California, have certain mechanical vibration standards that they have to measure up to before they can be built at any scale whatsoever. So what we're going to be doing here can be easily adapted to other situations besides the ones I mentioned. And usually all you have to do is just change your notation. Okay, so let's get the situation set up. We're going to start with a spring of length L, a little l. So let me go ahead and go over here and show you what that spring looks like. Okay, and the length of this spring, as I just mentioned, has the length L. Okay, so this has the length L as such. Okay, and that's called the natural length. And we're going to hook an object with mass m up to it. Okay, and that's what you see over here on the right hand side. So this um, this spring, the natural length, this is L, and when it's strung by our mass, of course it extends a little bit further. Okay, so what that looks like is we have some length L. Okay, and now we're going to extend this even further due to the mass and the presence of the mass by another length called capital L. Okay, so when the object is attached to the spring will stretch a length of capital L. Okay, and we will call the equilibrium position the position of the center of gravity for the object as it hangs on the spring with no movement. Okay, so a few other things I'm going to designate is this will be the equilibrium position, U, which equals 0. And I'm also going to designate the positive direction as downward motion. Okay, that's another key thing you need to note down for these mechanical vibration problems. So downward motion will be considered the positive direction. Okay, so as we described in the sketch, we're going to assume that all forces, velocities, and displacements in the downward direction will be positive. Okay, so all forces, velocities, and displacements in the upward direction will be negative. Also, As you can see in the sketch, we will measure all displacement of the mass from its equilibrium position, that is where u equals 0. And that will correspond to the center of gravity for the mass as it hangs on the spring and as at rest. And at rest, I mean absolutely no movement. Okay. So now we need to develop a differential equation, right? That will measure the displacement of the object at any time t, and also give the displacement of the object at any time t. So to do this, first we recall Newton's second law of motion, which is ma equals capital F, or F equals ma. Okay, so in this case, we will use the second derivative of the displacement for u for the acceleration. And so Newton's second law becomes mu double prime, which equals capital F, and we have three parameters that go into the force: T, U, U prime. Okay, and force is very much a vector, so this is a three-dimensional vector. Now, we need to determine all the forces that will act upon the object. There are four forces that we will assume that will act upon the object: two that will always act on the object, and two that may or may not act upon the object. And that'll be the topic for the next video.